Hi there, and welcome to this demonstration of Arctos Labs Echo Edge Cloud Placement Optimization. My name is Mats Eriksson, and I will guide you through this demonstration. Echo is a solution that helps optimizing edge compute networks by placing workloads in the most appropriate place. This can be done in initial planning stages, where the amount of infrastructure needed may be a question, or how do you design your application. It can also be used in provisioning phases where we're provisioning applications and services and want to make sure that they end up in the right and most optimal place to save costs. And that's also something that helps assurance to keep resiliency and constraints up and running. We typically have two demos. One is for provisioning and the other one is for infrastructure design, and this demonstration is about provisioning. The setup of the demo is so that we have built a specific visualization layer and control visualization layer to make it obvious what Echo contributes and the output from our engine. In this particular demo setup, we're using also open source Mono as the orchestrator that in turn controls 4 Openstack data centers. Hello and welcome to this demonstration of our Arctos Labs Edge Cloud Optimization technology. In this demonstration, we're going to use 4 different OpenStack data centers. They are captured here with their dashboards. You can note that one of them is fully utilized, so there's no available capacity there. At the bottom left part, you see the dashboard of the orchestrator, in this case an open source Mono orchestrator that does the mechanics of deploying workloads onto the data centers. You can see that there is one service already up and running. On the right hand side, you can see a control panel whereby we invoke new applications, new services to be deployed, give them particular parameters or constraints, and in the bottom right hand side you see a panel that illustrates, visualizes the output from our placement engine on the network topology, which is this part. And here you see the small yellow dots, that they represent how the already deployed application is being distributed across the cloud to edge continuum. You also see the cost that has been incurred as a result of deploying that particular first service. So moving onwards, we're now deploying a new service. In this case, it will be a telemedicine, again from a different location. We're specifying in this case we want to have 5 millisecond latency, and when we push go, it means we're sending the request onwards to our placement engine. The placement engine then calculates 2 different deployments. One is by just adding this request on top of what we already had. And remember now that this location in the middle here was fully utilized, so we cannot put any components there, which means that we have to push components further out into the infrastructure, thereby yielding a total new cost of 17K. So we have 2 services that kind of contributes the total cost. And this then is because there's a huge amount of data that needs to be sent. And we're also using what we refer to as the multi-service optimization, meaning let the engine calculate if it can move the already existing application, which you can see from the yellow indicators here that it did, to make room for the new request. This yields a totally lower cost of 7.6. So this would be a preferred and cost saving thing with taking the latencies into account. If we now continue, we can order another service from another place. Let's modify now the latency, so we also have a latency from and this represents the different components. So we now have latency constraint also between component 2 and component 3, which means that in this case, if we're only going to add this service, we need to put all the components out at the far edge, which is a costly option. Whilst if we can now again move components, we can create a more cost-efficient solution. And now we're going to deploy this solution, which means that we're now going to move, and we're fast forwarding here because this is about spinning up VMs in Openstack. So you could see here that the original service was deleted, and new services are up and running. The reason for having to delete an application, a service, is because open source mono cannot deal with migration. So we now have a new baseline where we have 2 applications that are up and running. They are distributed according to this illustration visualization here. There is 16.7K cost occurred. And now, if we now move on with the, we can now take away a data center. This means that, let's say this has a failure, it impacts one of the applications. We'll let the engine calculate what is the best mitigation of that problem. Well, it is by moving this component down here. The cost will increase, but we will keep the application constraints. And now we can also we can take that location back. And let's now imagine it's been repaired. And now this more central location disappears, and let the engine now again calculate how it can deal with the situation. And here it redistributes the components according to this. It's now an even higher cost of 32.8, but we keep the constraints, and we could now deploy this if we want to, but this is just for showing the system. And now we're adding another application, a digital twin from a certain location in the network. And now we have a third request coming out, and here again, if we're just adding this, we will incur a cost of 28K totally for all 3 applications. Whilst if we now again can move components, we can push down the blue component down here and make room for this one, which means it will be a lower cost totally. So now we can push go, which means we're now adding this application, and again we're fast forwarding time in the interest of you, of the audience here, because a VM takes some time to spin up. So it will soon be up and running, and you can notify the indicators of the different Openstacks.